We study X17Q. You can download the PDF file of this lecture note from kpop.org. Visit kpop.org and scroll down to find out K-pop physics. This is the X series, and you will find X16, 17 here. X17 fluid dynamics. If you click X, then you will find X17 lecture file, and C is X17C checkpoint, and we study today X17Q. And after recording this lecture, I will attach the video file in here, to giving link of our K-pop site, the YouTube K-pop. And from here, this is at K-pop at YouTube. You can click here to visit kpop.org. It's also possible. Okay, let's begin. A second. In the file X17 and Q, X17 and Q, and here you will find the details about number 1 and 2. So let me skip this one and study this number 3. The current density of a mass flow is given by this. As you notice, this vector field does not contain y and z components, and it does have only a single component. In addition, because J1 is a constant, this field is uniform all over the space. What is the divergence of the current density? Okay, why don't you visit here and click X to find that X17 file. X17, you will find all the details about the definition of the gradient operator and the gradient of a vector field and divergence, definition of the divergence, and curve. And you will know details about the current density. Then we shall find it is useful to study continuity equation, and this continuity equation will be considered after proving the divergence theorem. Once you know the divergence, what the divergence theorem is, then you can replace the volume integral of a divergence of a vector field as the surface integral over a closed surface S that is enclosing a given volume over a surface as this vector field scalar product with the surface element. All right. And by making use of this divergence theorem, you can replace this volume integral in terms of surface integral. And then, if you make use of the fact that current density multiplied by the surface element vector is just mass per unit time passing through the surface. If the surface is closed, then the current is positive then the volume contains some mass, and that mass depends on time, and the mass decreases because the mass flows out as time goes by. So it becomes the time derivative, negative time derivative of mass, and mass can always be expressed as the volume integral of density. As a result, we arrive at the differential form of the continuity equation. And this differential form of continuity equation is quite important in this chapter. Okay, so differential of form of this continuity equation, and here I copied this one. Wait a second. So using the definition of divergence, I can compute the divergence J. Divergence J is the derivative of the x component of this vector field with respect to x1. Derivative of the y component of this vector field with respect to x2. And the derivative of the z component of this vector field with respect to z. By the way, we do not have a j2 and j3. They are all vanishing. And j1 is nothing but the constant j0. So these two terms that disappear, and the first term survives. However, because j1 is j0, that is a constant, its a derivative is a 0. So we have a vanishing divergence. According to the differential form of the continuity equation, that is this, we have vanishing divergence. So time derivative of density is 0. So it is independent of time. Rho is independent of time. Still, it may have an x dependence, position dependence. We integrate over the volume, and here we put this integrate over the volume. Okay, in that case, divergence J, and right hand side, I can pull this time derivative out of this integral, and if we carry out the volume integral, density integrated over volume. This is nothing but the total mass contained inside the volume V. Mass m is contained inside this volume. Now its partial time derivative is the total time derivative because this m is independent of position. So what we obtain is, because divergence J is 0 all over the space, it is vanishing. As a result, mass inside the volume is time independent, so the time derivative of this mass is 0. Next, we consider a sphere of radius r centered at the origin. On the spherical surface, the current density of a particle is given by, it is a constant, and with uniform, this unit radial vector defined in the spherical polar coordinate. This is a spherical polar coordinate unit radial vector. And theta is the polar angle relative to the z-axis. This is a certain vector, and if you draw a vertical line onto the xy plane, there will be a straight line, and from the x-axis we can find the angle that is the azimuthal angle from the x-axis to this. Okay, so any unit radial vector is on the spherical surface toward the spherical surface. This unit radial vector is parameterized by the polar angle and azimuthal angle in this manner. So the question is, what is this? This is nothing but the continuity equation, but we remember the mass that this is different problem. We know the current on the surface of the sphere. But by the way, this question asked the volume integral of this divergence. But what we know is the boundary condition of the current density evaluated on the spherical surface only. It is impossible for us to evaluate divergence J. However, even if we do not know this integral, we can make use of the identity that is called the divergence theorem, and divergence theorem states that volume integral of the divergence, volume integral over, this is a volume, and we compute at every point inside this volume. This is the same as d sigma dot j integrated over the surface that is closed, and that is the boundary of this volume. So we can replace this volume integral as the surface integral. On the surface, I can evaluate this current. So we can solve this problem. Let's see. Divergence J is not known. However, we know what J is on the spherical surface. And on the spherical surface, we copy this current density here and multiply as a scalar product by the spherical surface. And the spherical surface is parameterized by radius squared d cosine theta d phi, where cosine theta runs from -1 to +1. Azimuthal angle phi runs from 0 to 2 pi. Okay, by the way, the surface element is the sigma vector, that is the sigma multiplied by ER hat. And the current density is also parallel to ER hat. As a result, the scalar product, this one, is nothing but J0 d sigma. And the directional, this scalar product is nothing but 1. Alright, so this is d sigma. And we don't have to worry about the direction anymore. We can carry out the integral over cosine theta and the integral over phi. And this part is independent of cosine theta and phi. As a result, we know what these integrals are. Cosine theta integral is 2, and d phi integral is 2 pi, and the product is 4 pi. So 4 pi r squared is the area of the spherical surface. As a result, what we obtain, this is, according to the divergence theorem, the left-hand side of this identity. As a result, this identity is a continuity equation. As a result, we can determine this. the value is 4 pi r squared g0. This integral is identical to this. Therefore, what is this? That is this. Okay. So number 5 is explained in the X17NQ. Please refer to X17NQ. Let's see. Oh, I didn't copy X17NQ. So you can go there. X17NQ is given in here. So that's it for today. Thank you.